Welcome back to the deep dive. This is where we, take some pretty dense source material and really try to pull out the core insights, the things you actually need to know.
That's the goal.
And today we're diving into, well, it's a pretty wild world where sound waves aren't just for hearing. They're used to create these incredibly extreme physical and chemical conditions.
Right. Right inside a little bit of liquid. It sounds like science fiction almost.
We're talking ultrasonics, sonochemistry, and then this really powerful combination called sonoelectrochemistry.
Yeah, it's genuinely one of the most surprising areas in modern physical chemistry, I think. Imagine like a tiny temporary star, thousands of degrees hot, hundreds of atmospheres of pressure.
Wow.
And you could basically create that and sort of control it just by flipping a switch and using sound. That's pretty much what we're getting into today.
Okay. So for you, the listener, our mission today isn't just the wow factor, right? We want to get into the mechanics.
Exactly. How does it actually work? We're going to unpack the fundamental concepts. We're drawing really heavily from a key text here, Introduction to Ultrasound, Sonochemistry, and Sonoelectrochemistry by Pollet and Ashokumar. Kind of the definitive guide.
Got it. Okay, so let's start unpacking. First things first. That term ultrasound, it covers a few different things. We need to define the three key fields our sources are really zeroing in on.
Okay, so the big umbrella term is ultrasonics. That just means sound waves with frequencies higher than about 20 kilohertz. So higher than what humans can hear.
Right, standard definition.
Then when you take those high frequency waves, pass them through a liquid, and they actually start causing chemical changes, that's when you're in the realm of sonochemistry. Sound-making chemistry happen.
Okay, makes sense. And the third piece, the one we're going to spend the back half of this deep dive on.
That's sonoelectrochemistry, or people often just call it SEC.
SEC, okay.
And SEC is where it gets really interesting, I think. It's the combination. You're using that power ultrasound, but you're integrating it specifically into electrochemical systems.
So systems where you already have electrodes, electron transfer happening.
Exactly. You've got electron transfer and chemical changes happening together right at that electrode surface, and then you add ultrasound to the mix. It's powerful.
Okay, but to understand how sound gets powerful enough to do chemistry, we need to classify it, right? The sources make a big distinction based on intensity.
A crucial distinction. Only one type really matters for the extreme chemistry we're talking about.
So what are the two types?
Well, first you've got high-frequency, low-intensity ultrasound, HFLI. This is usually up in the 1 to 10 millihertz centiwave wave range, but the key is low intensity, low power. Think milliwatts.
Okay, so where would you encounter that?
That's your standard medical diagnostic ultrasound.
Yeah.
The gel on the belly kind of thing.
Right.
And crucially, HFLI causes, well, basically minimal chemical or physical effects. It just doesn't have the oomph needed to kick off the really extreme processes.
Got it. So the workhorse, the one doing the heavy lifting chemically.
That's low-frequency, high-intensity ultrasound, LFHI. Or, more simply, power ultrasound.
Power ultrasound. And what are the specs there?
So the frequency is actually lower, typically 20 kilohertz, maybe up to 1 millihertz at. But the intensity, the power, is way higher. Hundreds, sometimes thousands of watts.
Okay, and that difference in power is everything.
That's everything. That high intensity is what lets LFHI drive these big industrial uses. Super effective cleaning, mixing thick liquids, getting valuable stuff out of materials, and actual chemical reactions, making new molecules.
Interesting. And just quickly, before we get to the chemistry itself, how is the sound actually made? You mentioned flipping a switch.
Right, the engineering bit. It all comes down to the transducer.
The transducer.
Usually the heart of it is a special kind of ceramic crystal, something like lead zirconate, titanate, PZT. It's called.
Yeah, PZT.
It's a ferroelectric material, which means it has strong piezoelectric properties. So you apply an alternating electric field across this crystal.
Zap it with electricity.
Yeah, basically. Yeah. And it physically expands and contracts very, very rapidly. It oscillates.
Yeah.
And if you tune that electrical signal just right, the crystal vibrates at the exact ultrasonic frequency you want, and that mechanical vibration pushes out sound waves, the ultrasound, into whatever liquid it's touching.
Clever. Converting electrical energy into physical vibration into sound waves.
Precisely.
Okay, so we've got the transducer making high-intensity sound waves, the power ultrasound pumping into the liquid. Now, here's the mind-bending part you mentioned earlier. The chemical effects, the energy, it doesn't come from the sound wave just like bumping into a molecule, right?
No, not at all. That's a common misconception. The interaction is far more dramatic, and it hinges entirely on one single, absolutely critical phenomenon, acoustic cavitation.
Acoustic cavitation, this sounds important.
It is the whole engine. If you remember one thing from today, make it this. Acoustic cavitation is this whole process. The formation, then the growth, and then the incredibly violent collapse of a microscopic bubble in the liquid that's being hit with the ultrasound.
A bubble, like an air bubble.
Could be air, could be solvent vapor, could be dissolved gases, a microbubble. And it's the collapse, that final sudden implosion. That's the moment it converts the mechanical sound energy into this focused blast of chemical energy, intense heat and pressure.
Okay. So we need to break that down. Formation, growth, collapse. Let's start with bubble nucleation. How does the bubble even form? You said the ultrasound creates pressure cycles.
Right. Alternating high pressure, compression, and low pressure rarefaction. It's during that rarefaction phase, the negative pressure part.
When the pressure drops.
Exactly.
Yeah.
The liquid effectively gets stretched. It experiences tensile stress. The sound wave is literally trying to pull the solvent molecules apart, fighting against the forces holding the liquid together, the cohesive forces.
And if you pull hard enough,
Pop. A tiny void, a bubble can form.
Yeah.
Now, for perfectly pure gas-free water at room temp, the theoretical negative pressure you'd need is enormous, hundreds of atmospheres.
okay, that sounds hard to achieve.
It would be. But the sources are really clear on this. In any real liquid, even clean water, you don't need nearly that much. Why? Because of impurities.
The imperfections.
Exactly. Tiny dissolved gas pockets, microscopic solid particles, specks of dust. These act like little weak spots or pre-existing nucleation sites. They make it much, much easier for a bubble to form and start growing when that negative pressure wave hits.
So the impurities are actually essential for cavitation to happen easily.
In practice, yes. They lower the energy barrier significantly. Now, once that tiny bubble exists, its life isn't simple. It starts oscillating, expanding, and contracting with the pressure waves. Its movement, its radiodynamics, is actually described by some pretty complex physics. Okay. The famous Rayleigh-Plesset equation is the model people use.
Okay, I've heard of that. It accounts for things like...
Things like how squishy the liquid is, the viscosity, damping effects, how heat moves in and out of the gas inside the bubble. It gets complicated fast.
Right. But the key thing is, it doesn't just oscillate evenly. It starts to grow. And the source calls this process rectified diffusion. This seems like a really important step. Why does a bubble that's pulsing in and out actually get bigger over time?
Yeah, this is a really neat bit of physics. Rectified diffusion means there's a net flow of mass, gas, or vapor into the bubble over many sound cycles. Even though it's pulsing, more goes in than comes out, on average.
How? What makes it biased towards growing?
The source points to two main mechanisms driving this rectification. They call them the area effect and the shell effect.
Okay, let's take the area effect first. What's that about?
Okay, think about the two parts of the cycle. Expansion phase, the pressure outside is low, so the pressure inside the bubble is low too. This pressure difference pulls dissolved gas from the surrounding liquid into the bubble.
Gas diffuses in.
Right. Compression phase. The outside pressure is high, the bubble gets squeezed, internal pressure goes up, and now gas is forced out of the bubble back into the liquid.
Okay, seems balanced so far. In then out.
But here's the trick. The size of the bubble changes dramatically. During that low pressure intake phase, the bubble is expanded, right? It has a larger surface area.
Bigger target for gas to enter.
Exactly. During the high pressure expulsion phase, the bubble is compressed, smaller, it has a smaller surface area. So over a full cycle, the area available for gas to diffuse in is larger than the area for it to diffuse out.
So more comes in during the big phase than leaves during the small phase. Mac game.
That's the area effect. More surface area for intake, less for expulsion. Simple, but powerful.
Okay, that makes intuitive sense. What about the shell effect?
The shell effect is a bit more subtle. It has to do with the concentration of gas in the very thin layer of liquid, the shell right next to the bubble wall. When the bubble compresses and pushes gas out, that gas momentarily saturates the liquid shell right around it. This reduces the concentration gradient between the bubble and the liquid slightly further away, which slows down how fast more gas can leave.
So it kind of clogs up its own exit route temporarily?
Sort of, yeah.
Yeah.
Then, when the bubble expands again in the next cycle, that saturated shell of liquid gets pulled away with the expanding bubble wall, exposing the bubble to fresh liquid that isn't saturated. This maximizes the concentration gradient for gas to flow in.
So the changing concentration profile near the bubble also helps push things inward on average.
Exactly. Both the area effect and the shell effect work together, causing this slow, steady accumulation of gas or vapor inside the bubble cycle after cycle.
And this growth continues until...
Well,
When? Does it just keep getting bigger forever?
no, it grows until it hits a very specific critical size. It's called its resonance size.
Resonance, like tuning a guitar string.
Very similar idea. The bubble reaches a size where its natural frequency of oscillation, how it wants to pulse in and out, perfectly matches the frequency of the ultrasound wave that's driving it.
Mm.
There's a simple rule of thumb relationship. The frequency times the resonant radius is approximately constant, about 3 days, 3 A's. So 4 at alto or approx 3d3.
And what happens when it hits that resonance size?
That's when things get dramatic. At resonance, the bubble absorbs energy from the sound field incredibly efficiently. Its pulsations become huge, really violent oscillations. It gets so big on the expansion phase that it can't effectively push all that accumulated gas back out during the compression phase. It overshoots.
It can't keep up.
It can't keep up, and the incoming compression wave from the ultrasound just slams into it. This leads to an incredibly rapid, uncontrolled collapse, the violent implosion.
The implosion, that's the main event.
That is the main event. That's our engine room. The collapse is so fast, nanoseconds, maybe picoseconds, that it's essentially an adiabatic process.
Adiabatic, meaning no time for heat to escape.
Precisely. No significant heat exchange with the surrounding bulk liquid, which is still relatively cool. All that kinetic energy of the collapsing bubble wall gets converted almost instantly into heat and pressure inside the tiny trapped gas vapor cavity.
And the conditions created are? Well, the numbers seem unbelievable.
They are staggering. Based on the fundamental physics, like the equations cited in the source, 1.8 and 1.9, the theoretical estimates suggest the localized temperature right inside that collapsing bubble core can spike up to 5,000 Kelvin.
5,000 K. That's hotter than the surface of the sun.
Yep, and the pressure. It can climb to maybe 150 MPa, which is about 1,500 times normal atmospheric pressure.
Wow. Okay, let that sink in. 5,000 degrees, 1,500 atmospheres, created just by sound waves collapsing a microscopic bubble, while the water in the beaker is still, like, room temperature.
That's the magic and the power of sonochemistry. It's non-thermal chemistry on a macro scale, driven by these incredibly intense but very localized and very brief thermal spikes.
Okay, 5,000 Kelvin is a number that definitely grabs your attention. But, theory is one thing. How do we actually know these temperatures are real? Do experiments confirm this?
That's exactly the right question. And the sources are careful to point out that while 5,000 K is a good theoretical starting point, those simple models often overestimate the actual maximum temperature achieved in many situations.
Okay, why the overestimate? If the collapse is adiabatic, shouldn't the physics be straightforward?
Well, adiabatic is an idealization. In a real collapsing bubble, the simple models often neglect some important energy loss pathways. For instance, some heat does conduct away into the liquid shell, even if it's fast. The gases inside the bubble also conduct heat.
Makes sense. Energy leaks out.
Right. And maybe the most significant factor they often ignore, especially if there are other molecules inside the bubble, is the energy used up by endothermic chemical reactions.
The chemistry itself uses some of the heat.
Exactly. If molecules inside the bubble are breaking apart, pyrolysis, that process requires energy. It absorbs heat. So some of the compressional energy goes into breaking bonds, not just into raising the temperature.
Okay, so theory gives us a ceiling, maybe. How do researchers actually measure or estimate the temperature inside this tiny, fleeting hotspot?
They use some really clever experimental techniques, mostly based on looking at the light emitted or the chemical products formed. And the temperature estimates they get actually vary quite a bit, depending on how the cavitation is happening.
Different conditions give different temperatures.
Yeah. For example, in studies of single-bubble sonoluminescence, SBSL, where scientists managed to trap and study just one stable, oscillating bubble, the temperature estimates can be truly extreme. They analyze the spectrum of the light emitted when that single bubble collapses, fitting it to a black-body radiation curve.
And the results.
The estimates there range from around 5,000 K, consistent with the basic theory, all the way up to, well, some estimates go above 50,000 K.
50,000 Kelvin, that's astronomical.
It is incredibly high, yeah.
Mm-hmm.
Why SBSL gets so much hotter than multi-bubble systems is still debated, but it might be because a single isolated bubble doesn't lose energy by interacting with neighboring bubbles.
Okay, but most practical applications, labs, or industry aren't dealing with single isolated bubbles, right? They have clouds of them.
Exactly. In the much more common scenario, which is multi-bubble sonochemistry or sonoluminescence, MBSC, where you have thousands or millions of bubbles forming and collapsing constantly, the temperature estimates are generally lower and perhaps more relevant for typical chemical reactions.
And what's the range there?
In MBSC systems, the experimental estimates usually fall somewhere between maybe 750 K and 6,000 K. Still incredibly hot, but a wider and generally lower range than the extreme SBSL numbers.
Okay, 750 to 6,000 K. That's still a huge range. How did researchers try to get a more precise number, like a quantitative measurement inside the bubble?
This is where some really elegant chemistry comes in. One of the classic methods, pioneered by Henglein back in the 80s, used methane gas as a kind of molecular thermometer.
Using methane to measure temperature. How does that work?
It's brilliant. They dissolve methane in water that was saturated with argon gas.
Hmm?
Argon doesn't react much. Methane is volatile, so it easily gets inside the bubbles as they form and grow.
Okay, so methane is inside the bubble, then it collapses.
Right. When the bubble collapses violently, the extreme heat inside causes the methane molecules to undergo pyrolysis. They break apart.
Heat breaks the chemical bonds.
Exactly. Methane, CH44, primarily breaks down into highly reactive methyl radicals, CH3
Free radicals. Unstable.
very unstable. So these methyl radicals immediately react with each other. And they can combine in a couple of main ways. One way is simple recombination. Two methyl radicals join to form ethane, C2H6 isn't sex.
Okay, CH3CO plus CH3CHO to C2H66.
Right. The other main pathway is a bit more complex. It involves disproportionation, leading to ethylene, C2H247, and hydrogen gas. Scully.
Okay, two different products from the same starting radicals. Where's the thermometer part?
The genius is in the kinetics, how fast these two competing reactions happen, specifically how their rates depend on temperature. This is governed by the Arrhenius equation.
Ah, Arrhenius. Rate depends on temperature.
Yes, but crucially, the two pathways depend on temperature differently. The formation of ethylene turns out to be highly sensitive to temperature. It has a very large activation energy. The exponential term in its rate equation is huge, like $134,000 JRT.
Meaning a small increase in temperature makes the ethylene reaction go much faster.
Exponentially faster. In contrast, the formation of ethane is much less sensitive to temperature changes. Its activation energy is lower.
Okay, I see where this is going.
Right. So if you carefully measure the amounts of ethane and ethylene produce the product ratio, ethane-ethylene, you can use that ratio, combined with the known Arrhenius parameters, to calculate backwards and figure out the effective temperature inside the bubble where those reactions happened.
That's incredibly clever. Using the product distribution as a thermometer, so what temperature did they find?
Using this method, Henklein's group estimated the core bubble temperature during methane sonolysis to be somewhere between 1930 K and 2720 K.
Okay, significantly lower than the 5,000 K theoretical maximum, but still very, very hot, much hotter than typical flames.
Exactly. It provided a much more chemically realistic number for these multi-bubble systems. And their work also revealed something really important and maybe counterintuitive about controlling these reactions.
What was that?
They found that the measured core temperature actually decreased if they increased the concentration of methane dissolved in the water.
Wait, more fuel made the fire cooler?
Kind of, yeah. It confirmed that the volatile solute, the methane, acts as an energy sink. When there are more methane molecules inside the collapsing bubble, they absorb more of the compressional energy as they break apart, endothermic pyrolysis. This dissipates the heat, leading to a lower peak temperature.
So the amount of volatile stuff inside directly moderates the temperature. That's a key control parameter.
Absolutely. It showed that the bubble's internal environment isn't just hot. It's a complex reacting plasma whose temperature depends on its contents.
Now, thinking about the structure of this hotspot, is it just one uniform high temperature inside? The source mentions work by Kenneth Susslich proposing a dual hot region model.
Right. Susslich and others argued it's more useful to think of two distinct, very hot zones rather than just a single core temperature, because different types of chemistry are likely happening in different places.
Okay, what are the two zones?
First, there's the gas phase zone. This is the true interior of the collapsing bubble, the core. This is the hottest part, the pyrolysis zone, where temperatures might indeed reach that upper range, maybe 5,200 PM, 650 keers, and pressures around $500 at Ampere. This is where volatile molecules are torn apart.
Okay, the super hot core. And the second zone?
The second zone is the thin liquid layer right at the interface, the shell of liquid immediately surrounding the collapsing gas cavity. This layer gets incredibly hot too, maybe around 1900 K, but it's different. It contains vaporized solvent, but also potentially non-volatile solutes that were near the bubble surface.
So a slightly cooler but still very hot interface region. Why is distinguishing this layer important?
Because it's the crucial transition zone. This is where the superhot gas core meets the bulk liquid. It's where high-energy radicals generated in the core first encounter solutes from the solution. A lot of important chemistry, especially for making materials, seems to happen right here in this interfacial shell.
Okay, so understanding that dual hot region model, the super hot core, and the hot interface leads us naturally to thinking about where different chemical reactions actually take place. The source uses a triple zone model, like in figure 1.3, based on where the molecules are and how volatile they are. This seems critical if you want to, design a specific sonochemical reaction.
Absolutely. Knowing where the action happens is key to predicting and controlling the outcome. Let's break down the three zones.
Zone 1, the hottest part.
Zone 1 is the hot interior gas phase. This is the pyrolysis furnace we just talked about, reaching maybe 5,000 K. If a molecule is volatile enough, like water itself, or dissolved gases, or volatile organic compounds like methane, it can evaporate or diffuse into the bubble during the expansion phase.
Gets trapped inside.
It's trapped inside. Then, when that bubble collapses, bam! Extreme heat and pressure tear those molecules apart. This generates the initial, highly reactive primary radicals.
Okay, and in just plain water, what are the most important primary radicals?
The big ones are hydrogen atoms and hydroxyl radicals.
Yeah.
They come from the water molecule itself being split by the energy. 2H dot plus OH dot. This is called homolytic cleavage.
Tenese glesalt and OH dot. Got it.
These two radicals are incredibly reactive. They are really the feedstock for almost all the subsequent chemistry that happens in sonicated water. They can rapidly recombine with each other.
To form stable stuff.
Yeah, for example, two hydroxyl radicals can form hydrogen peroxide, 2H10.H2022, or two hydrogen atoms form hydrogen gas, 210.HCl2. Or, and this is important, they can react aggressively with any other gases present inside the bubble, like dissolved oxygen, maybe forming atomic oxygen or even ozone, under the right conditions.
Okay, so zone 1 is radical generation central. Now zone 2.
Zone 2 is that shell or interface region we mentioned. That SIM 1900 Ka layer between the fiery core and the cool bulk liquid. What kind of chemistry happens here?
You said interfacial chemistry.
Exactly. This is the prime location for reactions involving solutes that are maybe not super volatile, so they don't readily go into the gas core, but they are surface active.
Surface active, meaning they like to hang out at the boundary between the gas bubble and the liquid.
Precisely. Like stope molecules, they tend to congregate at interfaces. So these molecules get hit with a double whammy. They experience the very high temperature of that interfacial shell during collapse, and they are the first things to get bombarded by the highly reactive radicals, diffusing out from the core.
So it's a unique reaction environment, hot and radical rich, right at the surface.
Exactly. And this is crucial for things like synthesizing nanostructures, where controlling reactions right at an interface is key. The source gives a really nice example from Cavalieri's group.
Yeah, tell us about that, the polyphenolic nanostructures.
Right. They were working with a molecule called N-benzoyl L-tyrosine ethyl ester, or BTTE. It turns out this molecule is surface active. So when they sonicated a solution of it, the BTTE molecules naturally gathered at the surface of the cavitation bubbles.
Okay, waiting at the interface.
Waiting at the interface. Then the bubbles collapsed. The BTTE molecules felt the heat of that SIM 1900 K shell, and they were hit by the outgoing K radicals generated in the core.
And what did that combination do?
The K radicals are powerful oxidizers. They attacked a specific part of the BTTE molecule, the phenolic ring, causing them to link together through biphenyl bonds, forming oligomer short polymer chains.
So the reaction was localized right there.
Yes. And then these newly formed oligomers, right there at the interface, spontaneously self-assembled into well-defined, stable nanoparticles with useful biological functions. It's a beautiful example showing how the combination of localized heat and radical attack at the interface can drive specific nanoparticle formation.
Very cool. Okay, so that zone 1 core and zone 2 interface. What about zone 3?
Zone 3 is simply the bulk solution. This is the rest of the liquid, far away from the collapsing bubble, basically at ambient temperature.
So how do reactions happen way out there if it's cool?
Reactions happen here if the solute molecules are both non-volatile, so they don't enter the bubble, and not surface active, so they don't hang out at the interface. They just stay dissolved in the main body of liquid.
Okay, so how do they react?
Their chemistry depends entirely on those primary radicals that are generated in zone 1, manage to survive recombination in zone 2, and successfully diffuse all the way out into the bulk liquid before they react with something else.
So only the hardiest radicals make it out there?
Pretty much. Since the bulk solution is cold, the reactions happening here are typically driven by these highly energetic escape radicals initiating chemistry at room temperature.
And the classic example the source gives is making gold nanoparticles.
Exactly. If you take a solution of gold chloride, OCl4 in water, and sonicate it. Gold ions are definitely not volatile, and they aren't particularly surface active. They stay in the bulk.
Okay.
But the collapsing bubbles are generating H-dot radicals, hydrogen atoms, in the core. Some of these H-dot radicals manage to diffuse out into the bulk solution. H-dot is a powerful reducing agent.
It wants to give away an electron.
Right.
Okay.
So when an escape dot radical encounters a gold ion, H solid plus in the OCl4 complex, in the bulk solution, it reduces the gold, OCl4 plus 3H dot to HTl plus 3H plus dollar. You get elemental gold atoms.
And those atoms then clump together.
They nucleate and grow into gold nanoparticles. So this is a perfect illustration of zone 3 chemistry, a non-volatile solute in the bulk reacting with a diffused radical from the bubble collapse. Pyrolysis inside, interfacial chemistry at the shell, and radical reactions in the bulk. 3 distinct zones.
Okay, we've spent a lot of time on the heat and the radical chemistry, which is fascinating. But you mentioned earlier that the collapse also creates immense pressure, 1,500 atmospheres. We can't ignore the purely physical effects of that, right? Especially for industrial scale stuff.
Absolutely not. Those mechanical forces are just as important, and sometimes more important, than the chemistry for many applications. The sheer violence of the collapse generates some dramatic physical phenomena.
Like, what does that pressure pulse do?
Well, for starters, it generates powerful, transient shock waves that blast outwards from the collapsing bubble through the liquid.
Like mini explosions.
Exactly like mini explosions. These shock waves carry significant mechanical energy. They're strong enough to physically disrupt molecular structures, break down aggregates, and importantly, they can shatter the boundary between 2 immiscible liquids, which is why ultrasound is fantastic for creating stable emulsions. Think mayonnaise, but made with sound.
Huh, okay. Emulsification. What else?
The shockwaves also contribute to erosion and pitting on solid surfaces immersed in the liquid.
And then there are the microjets you mentioned. Those sound particularly violent.
They really are. Microjets are maybe the most dramatic physical effect, especially near surfaces. They happen when a bubble collapses asymmetrically.
Not collapsing perfectly spherically.
Right. If a bubble is near a solid surface or even near another bubble, the collapse gets distorted. The liquid on the side, away from the surface, rushes in faster than the liquid near the surface. This asymmetry focuses the collapsing liquid into a narrow, high-velocity jet.
A jet of liquid shooting out.
Shooting inwards, typically directed right at the nearby surface, and the speeds are incredible. The source says up to 200 meters per second.
Wow, that's like bullet speed almost.
It's extremely fast for a liquid jet at that scale. And this intense, localized bombardment is what causes severe erosion, fragmentation of particles, surface pitting, and it's also fantastic for cleaning surfaces. It literally sandblasts things at a microscopic level. We'll come back to that cleaning effect in electrochemistry.
Okay, shockwaves, microjets. Anything else on the physical side?
Yes, there's also acoustic microstreaming. This is the fluid flow generated just by the oscillation of the bubbles, even the ones that aren't violently collapsing yet, or those undergoing stable cavitation.
Just the pulsing creates flow.
Yeah, the rapid expansion and contraction of the bubble surface acts like a tiny pump, constantly pushing and pulling the liquid right next to it. This creates intense turbulence and shear forces in the liquid immediately surrounding the oscillating bubble.
And why is that important?
Because this microstreaming acts as a very efficient form of localized mixing. It dramatically enhances mass transfer rates near the bubble and throughout the bulk solution, much more effectively than just stirring the whole beaker. This better mixing can significantly speed up reactions that might otherwise be limited by how fast reactants can get together.
Okay, so physical effects. Shockwaves for emulsification and erosion, microjets for intense cleaning and pitting, and microstreaming for enhanced mixing and mass transfer. Got it. Now, before we jump to applications, there's a light show.
Ah, yes, the light. Can't forget the light. The most fundamental type is sonoluminescence, SL.
Sonoluminescence. Light from sound.
Exactly. It's that faint, often bluish light that's emitted directly from the collapsing bubble itself. It's essentially black-body radiation. The gas inside gets so hot, thousands of Kelvin, remember, that it glows, just like the filament in an incandescent light bulb. The intensity and spectrum of the SL can even be used to estimate the temperature inside.
Cool. And there's a related effect that's useful for seeing where the action is.
Right. That's sonochemiluminescence, SEL. This is a bit different. It happens if you deliberately add a specific chemical agent, a chemiluminescent substance like luminol, to the solution.
Luminol, like they use in forensics.
Exactly like that. Luminol glows when it reacts with certain oxidizing species. In sonochemistry, the OH radicals generated by the collapsing bubbles react with the luminol, and that reaction produces light.
So the light comes from a chemical reaction triggered by the radicals, not directly from the heat.
Correct. And the advantage is that SCL is usually much brighter and easier to detect than the faint SL. But its real utility is in visualizing the cavitation activity.
How so?
If you take a picture of the SCL light being emitted from an ultrasonic reactor, like in Fig 116 in the source, you can actually see where the bubbles are collapsing most intensely because that's where the most SCL radicals are being produced to react with the luminol.
You get a map of the hot spots.
You get a map. And what these SCL images consistently show is that the active cavitation bubbles aren't just randomly scattered. They tend to concentrate in specific regions, namely at the antinodes of the standing wave pattern set up by the ultrasound reflecting within the reactor.
Okay, that's huge for designing reactors, right? You know exactly where to put things or how to shape the reactor to maximize the effect.
Absolutely vital for efficient scale-up in reactor engineering. You want the cavitation happening where it does the most good.
Okay, so with all these chemical and physical effects understood, where is applied sonochemistry actually being used now?
The applications are pretty diverse, but they tend to fall into a few main categories. First, environmental remediation.
Cleaning things up.
Yeah, leveraging those powerful oxidizing radicals, especially O2A0 and the H2OTO2 forms, to break down persistent organic pollutants in water. Things like phenols, chlorinated solvents like carbon tetrachloride, stuff that's hard to get rid of otherwise. Ultrasound offers a way to essentially incinerate these pollutants locally without high bulk temperatures.
Is that widely used?
It's mostly still at the laboratory or pilot plant scale, but the potential for advanced water treatment is definitely there. It's an active area of research.
Okay, what's another big area?
Material synthesis. This uses both the oxidizing and the reducing radicals, cation solvents or maybe alkyl radicals from organic solvents, generated by cavitation. Researchers are using sonochemistry to make all sorts of novel nanomaterials, metals, metal oxides, semiconductors, even bio-nanomaterials.
Well, why use sound instead of regular chemistry?
Often, the sonochemical routes are faster, operate at lower bulk temperatures, use fewer toxic reagents, and sometimes produce materials with unique shapes, sizes, or properties that you can't easily get through conventional methods because of those extreme localized conditions.
Interesting. And the third area you mentioned was food processing. That seems surprising.
It does, but it makes sense when you think about the physical effects. The food industry uses power ultrasound quite a bit.
For what?
Things like improving the texture and stability of dairy proteins. The shockwaves can gently modify the protein structures. It's used to enhance the extraction of flavors, oils, or antioxidants from plant materials. The cavitation helps break open cell walls. And it's great for making very stable emulsions and dispersions in food products, again thanks to those shockwaves and microstreaming, all usually without needing excessive heat that could damage the food quality.
Okay, so sonochemistry on its own, using sound to drive reactions in the bulk, liquid, or make materials is already pretty powerful. Now let's layer on the next level of control, combining that acoustic power with electricity. This brings us to sonoelectrochemistry, or SEC.
Right. SEC is specifically the study and use of that power ultrasound, 20 kilohertz to $1 millihertz, within an electrochemical cell. So you've got electrodes, an electrolyte, a voltage or current being applied, and you're blasting it with sound at the same time.
Is this a new idea?
The basic concept actually dates back quite a way. The source mentions Moriguchi exploring it back in the 1930s. But like a lot of sonochemistry, the field really took off more recently, maybe in the last few decades, as our understanding of cavitation and the measurement tools got much better.
Okay, so you have an electrochemical cell, typically a solid electrode immersed in a liquid electrolyte. How does adding ultrasound change what's happening, especially at that crucial interface between the electrode and the liquid?
The ultrasound affects both the bulk liquid, mixing, degassing, and the interface. But the effects at the electrode-to-electrolyte interface are usually the most dramatic and important. Remember those microjets we talked about?
The high-speed liquid jets from collapsing bubbles?
Well, when acoustic cavitation happens right next to the electrode surface, those microjets slam into the electrode over and over again. You also get intense acoustic microstreaming right along the surface.
So a constant physical bombardment and scrubbing of the electrode surface.
Exactly. And what's the single most important consequence of all that intense, localized agitation right at the electrode surface?
It must have something to do with getting reactants to the surface faster.
Precisely. It causes a massive thinning of the Nernst diffusion layer thickness, usually denoted by the Greek letter delta.
The Nernst diffusion layer, remind me what that is again.
It's this thin, relatively stagnant layer of liquid right next to the electrode surface. In normal electrochemistry, without aggressive stirring, reactant molecules or ions have to slowly diffuse across this quiet layer from the well-mixed bulk solution to reach the electrode surface where they can actually react, accept, or donate an electron.
So it's like a bottleneck for the reaction?
It's often the major bottleneck, yes.
Huh?
The rate of diffusion across this layer limits how fast the whole electrochemical reaction can proceed. This is called mass transport limitation.
Okay, so ultrasound, with the microjets and streaming, it just blasts that bottleneck away.
Essentially, yes, it violently disrupts and thins down that stagnant layer. Figure 2.3 in the source gives a good visual concept. By making delta much, much smaller, ultrasound drastically increases the rate at which reactants can reach the electrode surface. It massively boosts the mass transfer rate.
Okay, boosting mass transfer sounds like a huge deal for any process that depends on reactions at a surface. Let's stack up the benefits. What practical advantages does SEC offer? What problems does it solve?
Oh, the list is pretty compelling, especially for industrial applications. First, the intense agitation leads to very efficient degassing of the solution near the electrode. Removing dissolved gases like oxygen is often critical to prevent unwanted side reactions.
Okay, cleaner reactions. What else?
Continuous, aggressive cleaning of the electrode surface. Those microjets scour away any passivating films, reaction byproducts, or general gunk that might build up and block the active sites on the electrode. This is huge for preventing electrode fouling.
Fouling is a massive headache in industrial electrochemistry, right? Electrodes just stop working over time.
A massive headache. SEC can keep surfaces clean and active for much longer.
Okay, so degassing, cleaning. What about the actual electrochemistry?
Well, if you remove the mass transport bottleneck and keep the surface clean, the most obvious result is significantly increased electrochemical reaction rates and often higher product yields. Things just happen faster and more efficiently.
Makes sense. Does it affect the energy required?
Yes, critically. Because you're overcoming these limitations, the electrode reactions can proceed closer to their thermodynamic ideal. This means you often see a decrease in electrode overpotentials.
Overpotential. That's the extra voltage you need to apply beyond the theoretical minimum to get the reaction to go at a decent rate.
Exactly. It's like electrical friction or resistance in the system. If a reaction theoretically needs 1 volt, but mass transfer is slow or the surface is dirty, you might need to push it with 1.5 volts to get the current you want. That extra 0.5 volts is the overpotential, and it's wasted energy.
So SEC reduces that waste.
Correct. By improving mass transfer and cleaning the surface, SEC allows you to run the reaction closer to its theoretical potential, reducing $8 and therefore reducing the overall cell voltage needed. This saves energy, which is crucial for large-scale processes.
Better rates, higher yields, less fouling, lower energy consumption. That's a pretty good list. Anything else?
One more important one, particularly for electroplating and electrodeposition making coatings or materials. The physical agitation from ultrasound often leads to improved quality of the deposited material. You can get coatings that are harder, less porous, more uniform in thickness, and have better adhesion.
Okay, the benefits stack up really nicely, but if we want to actually use SEC effectively or compare different experiments, we need ways to measure and quantify these effects. What does the electrochemical response look like when you turn on the ultrasound? Is there a signature?
There absolutely is. The characteristic measurement is the current voltage curve obtained under ultrasonic irradiation, often called a sonovoltammogram.
Sonovoltammogram. Okay. What does it look like?
It typically shows a very distinct sigmoidal S shape, which is interesting because the shape is basically identical to the voltammograms you get using other well-established hydrodynamic electrochemical techniques.
Hydrodynamic,
like using a rotating disc electrode, RDE, where you spin the electrode really fast to force convection and improve mass transfer. The sonovoltammogram looks remarkably similar to an RDE voltammogram.
Okay, that's a useful comparison. And just like with an RDE, the important part of that S curve is the flat top, the plateau, right?
Exactly. That plateau current is the limiting current. It represents the maximum rate at which the reaction can occur under those conditions. When the reaction rate is purely controlled by how fast reactants can get to the electrode, it's mass transport limited.
And the key idea from before holds true. Ultrasound affects this limiting current how?
Dramatically. The fundamental relationship, confirmed by the source, EQ 2.1, 2.2, is that all limbs is directly proportional to the concentration of the reactant, and it's inversely proportional to that diffusion layer thickness.
Propto 1 delta.
Right. Since ultrasound massively decreases delta, The limiting current alum shoots up. You get much higher currents at the same concentration compared to a silent solution.
Okay. Now, here's something I found really interesting in the source material. It notes that under typical power ultrasound frequencies like 20 kilohertz, even relatively large electrodes, millielectrodes, say with a radius bigger than a millimeter, start to behave electrochemically as if they were tiny microelectrodes, radius less than a millimeter. How can a big electrode suddenly act small?
Yeah, isn't that cool? It's a fantastic illustration of just how dominant the local mass transport effects of ultrasound are. Microelectrodes normally have special properties, like high current densities, steady state behavior, because their tiny size naturally leads to very efficient, nonlinear diffusion of reactants towards them.
Right, geometry helps them.
Geometry helps them. But when you blast a larger millielectrode surface with intense ultrasound, the extreme localized mass transport enhancement from all those microjets and the intense microstreaming right at the surface completely overwhelms the normal diffusion pattern expected for its larger size.
So the acoustic flow dominates over the geometric diffusion.
Exactly. The mass transport characteristics become dictated by the intense forced convection caused by the sound, making the electrode behave as if it were experiencing the highly efficient mass transfer conditions normally only seen at a microelectrode.
That's wild. Okay, another detail from the sonovoltammograms. If you zoom in on that limiting current plateau, it's not perfectly smooth, is it?
No, often it's not. You typically see a series of rapid transient current spikes superimposed on the plateau.
Little bursts of extra current. What causes those?
Those spikes are thought to be the direct electrochemical signature of individual cavitational events happening right at or very near the electrode surface.
A microjet hitting the surface.
Precisely. Each time a high-energy microjet impacts the electrode, it causes an instantaneous, localized, and extreme disruption of the diffusion layer right at that spot. This momentarily boosts the mass transfer rate even further, resulting in a brief spike in the measured current. It's like seeing the individual hammer blows of the cavitation.
Okay, so we can see the effects clearly. Now, how do we move towards engineering control? We need models, equations that relate the cause, ultrasound power, to the effect, electrochemical current. How is mass transport quantified in SEC?
This is crucial for designing reactors and comparing results. For standardized setups, especially what's called the face-on geometry, where you have an ultrasonic horn pointing directly at a flat electrode surface, researchers develop relationships analogous to hydrodynamic equations. A key one is a Levitch-like equation, referenced as EQ 2.32.4 in the source.
Levitch equation. That's famous from IDE theory. So what does the SEC version tell us?
It provides a really practical link between the ultrasound parameters and the resulting limiting current. The key findings are that the limiting current is proportional to the square root of the total ultrasonic power being put into the system.
Okay, prop to score times. So doubling the power doesn't double the current, it increases it by about 40%.
Correct. It's a nonlinear relationship. And maybe even more importantly for reactor design, Galilum is inversely proportional to the square root of the distance between the ultrasonic horn and the electrode surface.
For prop to 1 square, so bringing the horn closer has a big impact.
A very big impact. Having the distance increases the limiting current by about 40%, same as doubling the power. This gives engineers direct levers to pull power and distance to control the mass transport intensity in their reactor design.
That's very practical. Is there a way to standardize the effect itself regardless of the specific setup?
Yes, and this is arguably even more valuable for comparing results across different labs and different types of ultrasonic equipment. This is the Pollet-Hein equation, EQ 2.5.
Pollet-Hein. What does that do?
What it cleverly does is it takes the easily measurable electrochemical data, specifically the limiting current density, which is linear to mole divided by the electrode area, obtained from the sonovoltammogram, and it converts that electrical measurement into an equivalent fluid velocity.
So it translates current density into how fast the liquid would need to be flowing past the electrode to give that same current density.
Exactly. It essentially says the mass transport conditions created by my specific ultrasound setup are equivalent to having the electrolyte flow past the electrode at, say, 0.5 meters per second.
Why is that conversion so useful? Why not just stick with current density?
Because acoustic fields are complex. A 20 kilohertz ultrasonic bath might deliver power very differently than a $500 kilohertz probe system, even if the total wattage is similar. Comparing Dallim values directly can be misleading. But by converting Dallim to an equivalent fluid velocity dollar, you get a standardized measure of the acoustic mass transport intensity that is independent of the specific frequency or equipment type.
Ah, so it allows for a true apples-to-apples comparison of the effectiveness of different ultrasonic systems.
Precisely. Researchers can use this method to map out the acoustic activity, the effective Doppler value, at different points within a reactor. It's absolutely crucial for standardizing measurements, reliably comparing results from different studies, and successfully scaling up processes from a small lab beaker to a large industrial reactor.
Okay, that sounds like a really powerful tool for the field. Let's shift gears slightly. We've talked a lot about mass transport getting stuff to the electrode. What about the actual chemical reaction itself, the electron transfer step at the surface? How does SEC affect the kinetics of that step, measured by the heterogeneous rate constant, cotiller dollars?
Now this is where things get a bit more nuanced. And the literature actually shows some conflicting results. It's not as clear-cut as the mass transport effect.
Okay, what are the different findings?
Well, some studies have reported an increase in the intrinsic rate constant Cato dollars under ultrasonication.
And what's the explanation for that? Faster chemistry.
The usual explanation is the localized heating effect. Remember that SIM 1900K interfacial hot zone. Even if the bulk is cool, the electrode surface itself might be experiencing transient high temperatures during cavitation collapse nearby. And higher temperatures generally make chemical reactions go faster, including electron transfer. So faster kinetics due to local heat.
Makes sense. But you said conflicting results.
Yeah. Other researchers looked carefully and found no significant effect of ultrasound on Kellar wave for the systems they studied. The electron transfer rate itself didn't seem to change.
Okay, so maybe the heating effect isn't always dominant or measurable.
Possibly. And then to make it even more confusing, some studies have actually reported a slight slowdown in the electron transfer kinetics for certain types of reactions, usually quasi-reversible ones, under ultrasound.
A slowdown? How could ultrasound make the reaction slower?
The proposed reason here isn't temperature, but rather that aggressive physical cleaning effect we talked about.
The microjets being too effective.
Potentially, yeah. The idea is that the constant scouring of the surface by microjets might be continuously removing crucial reaction intermediates or preventing the formation of an optimal surface structure or adsorbed layer that's actually necessary for efficient electron transfer in that specific reaction.
So it's a balancing act. You
Yeah.
could get faster mass transport, maybe some thermal acceleration, but you might also be physically disrupting the surface chemistry needed for the electron transfer itself.
Exactly. It seems to depend heavily on the specific electrochemical system, the reaction, the electrode material, the conditions. You might get a boost from heat or no effect, or even a slight inhibition from overcleaning.
Interesting complexity. What about other kinetic indicators, like the half-wave potential on the sonovoltammogram? Does that shift?
Yes, shifts in E12 are commonly observed. Remember, E12 is the potential where the current is half of the limiting current, and it gives an indication of how easily the reaction proceeds thermodynamically and kinetically.
So why does it shift under ultrasound?
The sources suggest a couple of main reasons. One possibility is chemical irreversibility introduced by those reactive old-age double radicals. If the radicals react with the electroactive species or its products near the electrode, it can change the overall reaction pathway and shift the potential.
Okay, side reactions changing things. What's the other reason?
The other, perhaps more common explanation goes back to the surface cleaning and activation. By constantly removing oxides or adsorbed inhibitors, the ultrasound is essentially presenting a more active, cleaner electrode surface to the reactants. This cleaner surface might allow the electron transfer to happen at a potential closer to its true thermodynamic value, thus shifting G12
Okay, this has been a fascinating dive into the mechanics. We've seen how sonochemistry creates these extreme local conditions via bubble collapse, and how sonoelectrochemistry harnesses that physical power, the microjets, the streaming, to dramatically enhance processes at electrode surfaces. Let's wrap up by looking at the broad range of applied sonoelectrochemistry. What's the final utility stack here? Where is this technology making a difference?
The applications are really diverse, touching pretty much all areas where electrochemistry is used. As we mentioned, it's a valuable tool just for fundamental research, like accurately measuring mass transfer coefficients in unusual solvents where standard methods might fail.
Okay, basic science tool. What about industry?
Big impact in metallic coatings. Things like electroplating, electroforming, electrocrystallization. SEC is used to get coatings that are denser, harder, more uniform, adhere better. Essentially, higher quality metal layers. The microjets help ensure fresh reactants reach the surface evenly and knock off any poorly adhering deposits.
So better chrome plating, for example?
Could be, yeah, or other metals. It's also used to enhance the co-deposition of particles within a metal matrix, like embedding tiny ceramic nanoparticles into a nickel coating to make it much harder and wear-resistant. The ultrasound helps keep the particles suspended and forces them onto the electrode surface during plating.
Very cool. Where else does that aggressive physical action find use?
Well, kind of the opposite of plating. Accelerated corrosion testing.
Making things corrode faster.
Yeah.
Why?
To test materials. If you want to know how a new alloy will hold up over 20 years in seawater, you don't want to wait 20 years. By using SEC, the microjets constantly strip away any protective passive layers that might form on the metal surface, forcing it to corrode much, much faster. It allows researchers to rapidly screen materials and predict long-term durability.
Clever. Using the destructive power for predictive testing. What else?
It's finding use in organic synthesis, particularly for reactions that might be sluggish or require harsh conditions conventionally. SEC can offer cleaner pathways, sometimes driven by electrogenerated radicals combined with the enhanced mass transfer. Also in the synthesis of specialized polymeric and metallic nanomaterials, similar to sonochemistry, but with the added control of electrical potential.
Okay. And you mentioned environmental applications earlier for sonochemistry. Does SEC play a role there too?
Yes, definitely. There's work on using SEC for water disinfection and treatment. The combination of electrochemically generated disinfectants, like chlorine or ozone, with the physical disruption and radical generation from ultrasound, can be very effective at killing microorganisms and degrading pollutants.
And finally, a really critical area for the future, energy.
Absolutely. This is a major focus, and one where the authors of our source text have significant expertise. SEC is being heavily investigated for improving energy production and storage technologies.
Like what specifically?
For instance, the efficient production of useful gases, most notably hydrogen through water electrolysis. Enhancing mass transfer with ultrasound can lower the energy needed to split water, potentially making green hydrogen production more economical.
Making electrolyzers work better.
Exactly. And also for fabricating better electrodes for these devices. Using SEC during the process of making electrode materials for electrolyzers or fuel cells can create surfaces that are highly porous, have high surface area, and are very active catalytically. This leads to devices that perform better and last longer.
So better coatings, faster testing, greener synthesis, cleaner water, more efficient energy. It really is a broad impact.
It cuts across a lot of fields.
So looking back at this whole deep dive, the core takeaway seems to be that sonochemistry and sonoelectrochemistry give us this unique toolkit. It's a non-thermal approach overall, but it uses sound to create these tiny pockets of absolutely extreme thermal and physical conditions, right where we need them, allowing us to accelerate or even fundamentally change chemical and physical processes by manipulating bubble dynamics.
That sums it up pretty well. We're using acoustics to engineer events down to the molecular level, especially at interfaces in the case of SEC. That ability to drastically thin the diffusion layer maybe by a factor of 100, while simultaneously providing localized high temperatures and intense physical mixing right at that crucial molecular interface, that combination is really unique and powerful.
Yeah, it really is. Which kind of leads us to the final provocative thought for you, the listener, to mull over. We've seen that we can generate these extreme conditions, thousands of degrees, hundreds of atmospheres using just sound waves, and we can localize them pretty well. So the question is, what truly unexpected transformations might become possible, maybe in medicine or in designing new catalysts or creating entirely novel materials if we learn how to engineer and control these collapsing microenvironments with even greater precision, like pinpoint spatial control, perfect temporal control?
Right. If we could place and trigger these nanoscale explosions exactly where we want them, when we want them, what could we build? What could we change?
How far can we really push the acoustic control of matter at this level?
It's a fascinating question. It's something that researchers in this field are actively exploring. Definitely something to keep an eye on.
Indeed. Well, thank you for guiding us through that powerful world of collapsing microbubble.
My pleasure. It's always fun to talk about.
And thank you for joining us. We'll catch you next time for another deep dive.